Hello everyone. We'll get started with this fourth module of this advanced reinforced concrete design. In this module, we're going to discuss the behavior under pure axial loads, basically how the reinforced concrete members are going to behave when it is subjected to axial compression and axial tension. Okay, so what are the expected learning outcomes are? Uh, how this basic laws of mechanics can be used to describe the concrete behavior. So we'll talk about that and then explain the low displacement behavior under pure axial compression and tension. And we will also try doing some calculations for different increments of strain. And we will also try to vary the concrete strength and then the amount of steel. And we'll try to explain what is the role of concrete and steel in under the behavior of axial loads, particularly how is it going to contribute in compression and tension. And we'll also take one example. We'll compare the behavior when we use low strength concrete and high strength concrete, how the behavior is going to change. Okay, so differentiate the behavior between normal and high strength concrete. Right. So usually, the external loads are applied on the structural systems, and these external loads manifest in the form of internal forces. These internal forces can be broadly classified as axial forces, which could be compression or tension, or bending. Bending can be about both axes, and also you can have members that are subjected to shear and then torsion. Okay. Now the axial forces can be either compression, that is going to squeeze the member and putting it in compression, or it's going to elongate the member and it's going to putting it in tension. So that like the one that we have seen here. Okay. So this is going to be the focus of this present module. We'll take plain concrete, we'll take reinforced concrete, and then we will see how these members are going to behave under compression and tension. Right. So when we talk about pure axial loads, usually concretes are very strong in compression, right? And then they are weak in tension. We have seen that the tensile on the concrete is, it varies depending upon whether it is an axial tension or flexural tension, but usually they are very low. It is about 10 percentage for axial uh, loads. Okay, so for example, if you look at this kind of a frame, what we have is beams that will be usually come under the combinations of bending moment, shear force, and torsion. The axial force are very limited. If you have axial force, then you call them as a beam column member. And column members, they are usually under combinations of axial loads, bending. Bending can be about both axes, and then you will have shear forces, and then you will have torsion. Sometimes, if the structural system is not designed to reduce the torsion at the global level, then you will also have, depending upon the way the loads are getting transferred, sometimes you will have torsion in columns as well. Now we can also have bracings, but usually these bracings are provided in the form of steel members, uh, but they will be subjected to pure compression or pure tension. And sometimes, we also use these kind of systems. This is a tied arch bridge, which is a very famous structural system for bridges. And you see that these members are called as tie members, which will be under tension. So reinforced concrete members also can be designed to resist this kind of tension that is coming into the system. Okay, but usually RC members are not very efficient in resisting tension. So we need to make sure that also we have talked about in the last module about durability. In tension, we make sure that it is not going to crack extensively and lead to corrosion and other durability issues. That aspect we need to be very careful when you have members that are subjected to pure tension. Okay. Similarly, the reinforced concrete truss systems are also sometimes used. Okay, especially in industrial factory building, just like what you have trusses. So there also sometimes you'll have tie members that will be subjected to tension. Right, now let's look at the very simple example that what we're taking is a simple concrete prism, and what we are having is this is basically, you can write, say this as a concrete and this is basically a rebar. Okay, so this rebar, okay, so when it is subjected to axial load, you can replace the concrete and rebar as two springs because they're all connected together, right? And two springs that are connected in parallel. Okay, that I'm representing the stiffness of, let's say, concrete as Kc and steel as Ks. Okay, now when it is subjected to this axial tension, now you see that basically they are going to stretch, and when they are going and undergoing stretching force, you can see that initially at this location it has gone up to this. Okay, so what does that take? So this is the deformation that we are having or putting it in the this RC system. Now you see that both the springs, when I'm trying to idealize the concrete as a spring with a particular stiffness, of course that stiffness depends upon what is the area and what is the elastic modulus of that concrete. And similarly, the steel rebar also, it is having some stiffness. Both of them are undergoing same amount of deformation. So what does it tell? They undergo under axial loads, they undergo same deformation. That is one thing that we need to know. So it is initial length was L, now it is stretched and it has become L plus delta L, or we can also say that deformation is delta L. Okay, right? Now, if you from this free body diagram, when you look at it, so you can express this applied load as what are the resistance that is coming from concrete plus the resistance that is coming from steel. So because these two things are acting in parallel and the load resistance can be expressed. So you can take a small free body diagram like this. So it is going to be like this. Okay, and both of them are connected like this. So this is your applied load P, and this resistance will come from concrete, and this resistance will come from steel. So when you put your horizontal force equilibrium, P will be equal to PC plus PS, the load resistance by concrete plus load resistance by steel. So that's what we're doing. Okay, let me erase this. Right. So we can see that the total elongation in the system, that is delta L, both the springs, concrete as well as steel, they undergo by the same deformation. So we can write the compatibility deformation as the total elongation delta L is same as that what is happening in the concrete and same what is happening in the steel. So that in other words, elongation in steel and concrete are same because they are under axial tension. So this is equilibrium of internal forces. This is the fundamental law of mechanics. The structural system should always satisfy equilibrium. And in addition to that, we are also enforcing that both of them are undergoing same deformation. So that ensures that concrete and steel are undergoing same deformation. When deformation is divided by the length of the member, you get average strain. So there is a strain in the concrete and steel is also going to be same. So that is, we can call that as strain compatibility. Okay, right. Now, for example, let's say this is a prism that we are taking. For example, I'm just taking this length as, let's say, 1000 millimeter or 1 meter. Okay, and I'm subjecting it to tension. So, at any point of time, we know that to satisfy equilibrium from the previous slide, we have seen that the applied load P should be equal to the load in concrete plus the load in steel. Okay. For example, I've taken this cross section to be 250 mm by 250 mm. Okay. And it is also this red color is basically your steel. This is nothing but your steel rebar. Okay. So for convenience sake, anyway, it's an axial load. So we have just put as a one rebar. But if you look at it as a column member or tie member, of course, you'll have multiple rebars. Now I'm clubbing everything and showing it as a one reinforcement. Okay. Now we know that how do I get my PC and PS? That is a load resistance from concrete and load resistance, load resisted by steel. How do we get it? So we know that if somehow if we are able to find the stress in the concrete, stress multiplied by the area of concrete will give me what are the load resisted by concrete. Similarly, if I know what the stress, because both of them are undergoing same level of strain, right? That also you have to keep in mind. And if the steel, if I know the stress in the steel, again stress multiplied by the area of steel will give me what is the load resistance by the steel. So if I'm somehow able to get the stresses, because cross-section details will be given to us, or when you are designing it, you are going to assume it, certain area of concrete section and certain area of steel. So that will be given to you. So then we can calculate what is PC and PS if you know what are the stress in the concrete and steel. So generic equilibrium equation can be written as the applied external load should be equal to area of concrete multiplied by the stress in the concrete plus area of steel multiplied by stress on the steel. Now the question is, how do we get these stresses? So what are the condition we know? We know both concrete and steel are stretching by same magnitude. Okay, so or in other words, we can also say this as the strain in the concrete will is also equal to strain in steel. So this is your compatibility because they're stretching by the same magnitude, right? So what is it I should do then? To calculate the stresses, I should be expressing the stresses in terms of strain. So compatibility condition tells me that the total strain epsilon is equal to strain in concrete, which is equal to epsilon s. Okay, right? We have seen that. Similarly, what is the total strain in the member? It is nothing but delta is nothing but epsilon times the length of the member, which is again epsilon c multiplied by length of the member, is again epsilon s multiplied by length of the member. Okay, so this is a strain in the all of them are undergoing same strain. So we can also invoke that if your materials are in the, so how do you relate stresses and strain? Stresses and strain are related by their constitutive relationship. These are basically material properties. Okay, if I give you strain, and we should be able to give you stress depending upon the constitutive relationship that we have discussed in the material chapter. Okay, for example, concrete, we have different models: parabolic model, Thorenfeld model, and a lot of other models are also available for describing the constitutive behavior of concrete in compression. Similarly, steel also we have seen. You can have a bilinear model, elastic, perfectly plastic model, or elastic hardening model. So many other idealizations of stress strain curve for rebars are also available. Right. So if the material is, if the strain levels are very low, both concrete and steel can be in the elastic limit, then we know that from Fuchs law, the stress in the material will be elastic modulus multiplied by the strain in the material. So FC can be expressed as epsilon C, sorry, EC multiplied by epsilon square. EC is the elastic modulus of concrete. Again, EC, you know, we can calculate using 5000 square root of FCK from code point of view. Okay, or in other words, it's elastic modulus of the material. Similarly, stress in the steel Fs can be written as Es multiplied by epsilon s, where Es is the elastic modulus of steel, which is going to be 200 gigapascal or 2 into 10 to the power of 5 megapascal. Usually for steel rebar, the elastic modulus doesn't change. For concrete, EC will change depending upon the grade of concrete that we discussed in the material chapter. Right. So because now steel and concrete are undergoing same strain, what I can write is from your this equation. Now, what is FC for very low strain? So this is applicable for very low strains when the material is under elastic limit. Okay, so we can write this as P is equal to AC multiplied by EC, and the strain, because strain in concrete and strain in steel are same. So when I put it in this equation, FC as EC and epsilon C, and in this equation, right? So in this equation, Fs can be written as Es multiplied epsilon s. Now we know that epsilon c is equal to epsilon s, so that is equal to epsilon as per here. So epsilon can be taken out, and you can write it like this. Okay. So in this way, for very low strain, the load deformation behavior can be written. So you can see for very small strains, now the load can be expressed as load resistance can be expressed as area of concrete multiplied by elastic modulus plus area of steel multiplied by elastic modulus of steel. The whole thing multiplied by delta by L. Okay. Now again delta, if you want, you can calculate from the strain as strain multiplied by length will give you the deformation. So that's what we have seen it here. Okay. That's what we have written here. Okay. Or in other words, if you want to replicate this for larger strains also, then we don't know up to what level that material is going to be elastic. So if you want to write it in a very generic way, you can write that as AC multiplied by stress, which is function of your strain, the assumed strain. Similarly, for area of steel multiplied by stress, which is again function of your strain. Okay. So if I know the constitutive relationship of concrete and steel, then I can find out what is the load resistance of the structural member for a particular assumed strain. Similarly, the deformation is the assumed strain multiplied by the length of the member. Of course, you can see when the material is undergoing, you will have a lot of crackings also. Okay, so you will have after certain strains, the concrete will not fully be able to contribute. We have discussed in the material chapter. There is a phenomenon called tension stiffening. Okay, so at the crack location, only steel is taking, but between the cracks, the concrete is also resisting some level of applied tension. Okay, but however, for the global calculations in a simplified manner, we are saying that the average strains are same in both concrete and steel at the in an average sense. Okay, so now, so for an assumed value of strain, how do I get the stresses? So this is what we discussed in the previous chapter also. So these are constitutive relationships. So that is going to relate the stresses and strain. So this is the stress strain curve behavior for concrete cylinder. Now you can ask me, why are we taking this parabolic stress strain relationship? Okay, so if you look at IS 456, it gives you parabolic and then you have straight portion. But if you test a cylinder of concrete which are lesser than 40 megapascal in strength, usually the behavior can be approximated with these relationship that we discussed in detail in the material chapter. This is also called as parabolic law, or it's also Hognestad's stress-strain relationship for concrete in compression. Okay, as we have seen, epsilon prime c corresponds to the strain corresponding to peak strength. Okay, usually up to 40 megapascal, we take that value as 0.002, and F prime is your peak strength of your concrete when it is tested in as a cylinder. And we have also discussed it, when you test it as a cylinder, you get the true representation of the material. And we also talked about what is the size effect and other things. But F prime C is the actual material strength. And for that, you need to test a cylinder of at least aspect ratio of 2. What is aspect ratio? Again, length to diameter ratio. Okay, we have discussed all those things in the material chapter. So, right, so this is the relationship that we are going to have. So you see here, you get a nice you get this nice relation. So you get this nice parabolic relationship. Okay. Similarly, how the concrete is going to behave in tension, we've studied that. Doing pure tension is always difficult. So either people do modulus of rupture test, or people do splitting tension test, which is also called as Brazilian tension test. Okay, so you can get, and we've seen that the tensile strength, which is written as F prime T, is roughly we are taking that as 10% of your compressive strength. Of course, it's going to vary depending upon what kind of concrete you have. It is going to vary from 8 to 15%. But for simplicity here, we are taking the tensile strength as about 10% of your compressive strength. Okay, right. So this is the relationship for concrete we are going to use for up to 40 megapascal in strength in compression. Now we know that in steel, if you test your steel rebar, again, depending upon whether you are having a mild steel or you are having a deformed bars of 415 or 500, the stress strain characteristics is going to change. But from design point of view, usually we limit your design to the yielding of steel, and any strength, the strain hardening capacity that what we are going to get, we will not count them in terms, just to be conservative in calculating our capacity. So that is why this kind of a bilinear relationship is reasonably, it is good for calculating the capacities. Okay, unless we are doing some experiment, we want to predict the capacities exactly, then what we need to do is we have to test the rebar and get the stress strain relationship, that we have to use it. But otherwise, for simple calculations, we can, this kind of bilinear approximation is reasonably good enough. Okay, and we have seen that at a strength of about 500 it starts yielding, right? And then after yielding the stress does not increase much, so we can assume it to be constant. That is your elastic perfectly plastic assumption for a sustained curve for steel. And steel, as you know, that it is both effective in compression as well as in tension. But in compression we need to prevent the buckling, and column members especially, we need to make sure that we are having adequate transverse reinforcement and so on. That we'll discuss when we talk about column design in the chapter on columns. Okay, so this is the constitutive relationship for steel as a reinforcement that we are going to use in our calculations. Okay, right. So why we are doing this? Because the load I have to get it by stress in material multiplied by the area. How do I get the stress? Because we know from compatibility, I know what is the strain. For a particular strain, I want to calculate the load distance. So that's why we need to link the stresses and strain, and the stresses and strains are linked through your constitutive relationship. So the usually for any rational model, we use three fundamental laws of mechanics. Okay, which are it has to always satisfy equilibrium. In this case, we are talking about axial force equilibrium, and then it has to satisfy strain compatibility or compatibility of deformations. And the third one is we also need to satisfy or follow some constitutive relationship of the material. Here we are dealing with reinforced concrete, so concrete should follow some constitutive relationship in compression and tension. Similarly, for steel also we need to follow some stress-strain relationship in compression and tension. Right. So this is your constitutive model. Okay. So fine. So if you look at it here, and now let's look at intention how the plain concrete is going to behave. Okay, and we have seen that when I'm pulling this concrete and it is going to fail at a low load values or low stress values. Okay, so in this case I am taking a simple concrete prism. Again, you can take this value as, let's say, 250 by 250, because these are the dimensions that we are going to use in our further calculations, right? So when it is subjected to tension, we find that, again, if I'm taking, let's say, 40 megapascal concrete, and what is the tensile strength of concrete? It is going to be roughly 10%. It is going to be 4 megapascal, right? So it is going to go like this, and it is going to fail. So in this case, I've taken a let's say 20 megapascal concrete. So that's why when the stress levels are at 2 megapascal, and how do I get the stress for applied load? P is applied load divided by the total cross section of the section, that is 250 by 250 will give me what is the stress for any point of load P. If I know the cross section area, applied load divided by the area will give me the stress. So when it reaches about 2 megapascal, you will have a one big crack that will form. That's it. That member concrete prism cannot take any load. Okay, so this is your pre-cracking, and then suddenly it is going to rupture. Okay, now let's look at how the reinforced concrete is going to behave. Okay, so reinforced concrete in tension will have three stages. One is pre-cracking, and then after cracking, again, you will not have a sudden failure because now you have reinforcement. So the reinforcement is going to take the load. So you will have post-cracking and pre-yield, and then when you keep on stretching that member, then the rebar also will yield, and then it will keep on resisting, because the steel, even after yielding, it can keep on resisting the applied load until it further, finally it fractures, right? Through plastic deformation. So this is how the behavior is going to be. So you see, it's not going to fail at 2 megapascal, unlike same prism 250 by 250. Now what I've done is I put some steel. Okay, so when I'm stretching it, so this is the kind of behavior that I'm going to get, and you're going to get very large stresses can be transferred in an average sense. Okay, and then you'll have yield. Finally, it will go and rupture when it is rebar is getting fractured. Okay, so this is the kind of behavior that we get. So by adding little bit of amount of steel, we can really get good amount of increase in tension capacity. So that is the beauty. We know that concrete is weak in tension, so wherever it is going to develop tension, we are going to put steel that is going to help in resisting the applied load. That we'll see. Okay, this is the cracking and this is the yielding. This is what is it. Up to pre-cracking, you have one stage, and then what we have is, okay, so up to this you have one stage, and then you have this. So this is your yield. So this is your stage 2, and this is your stage 3. Okay, so this is your first stage, Okay, and this is your second stage, and this is your third stage. So it has three stages. Okay, so this is your first stage. Okay, which is where you're going to have large elastic stiffness as a member. Right. So if I want to plot this axial load deformation behavior, now how do I go about it? If your section details are given to you, if your member length is given to you, if you also know the amount of steel that is there, and here only the longitudinal bar is going to help in resisting the applied load. The ties, okay, that also usually concrete members will have tie or a transverse reinforcement, but that influence will be there, some influence will be there. It is going to confine the concrete core, that effect of confinement of ties, all those things that we'll discuss in the chapter on column behavior. But for now, we are saying that the tie is not going to really play a major role. The majority of the load resistance is going to come from longitudinal steel and concrete. Okay, so these are the steps that we are going to follow. We're going to choose the value of concrete strain to establish this load deformation behavior. And then, once we assume that strain is at the member level, again we know that epsilon is equal to epsilon c, which is equal to epsilon s. That means the the strain is in the member will be equal to strain in the concrete, which is equal to strain in the steel, right? And find the, so once we this is your strain compatibility. So if you assume your epsilon, that is the same strain that is going to be in concrete and steel, because both of them are, we are assuming that it's going to have a perfect bond. Both of them are going to deform by the same magnitude. Okay. So then you find the concrete and steel stresses through this constitutive model that we have discussed in the previous slide. And once you know the stresses, we know that load can be calculated as, what is it? It is going to be Fc multiplied by AC plus Fs multiplied by As. Okay. So the key is to find stresses. Okay. That's what. So then you can calculate. Then axial deformation can be calculated as delta can be calculated as assumed strain multiplied by length of the member. So for any assumed value of epsilon, you can get one value of load and we can get one value of deformation. In that way, by keep incrementing this strain values, you can generate the entire load deformation behavior both in compression as well as in tension. Okay, so this is one quick example. Of course, we'll solve it also for particular strain values. But if I'm taking, in this case, I'm taking a section with 250 mm by 250 mm, and it is a member actually. It is having 1 meter length. Okay, the length of the member is 1 meter, and the section dimensions are 250 mm by 250 mm. It is having a concrete cylinder strength of 35 megapascal. So what is concrete cylinder strength? We denote it as F prime C. Okay, and FCK is your characteristic strength, and FCU is cube strength. And what is the relationship between cube strength and cylinder strength? Cube strength is higher, which is 25% is higher than your cylinder strength. So you should know all this. Because we are talking about behavior, we want to use the actual sustained curve behavior, that what you're going to get when you test a cylinder in your lab. Okay, so let's not worry about what the IS code says for sustained curve and so on, because that is from design aspects. Okay, now we are trying to understand the behavior, how the systems are going to behave, what is the role of concrete, what is the role of steel. So for this, we will use the actual behavior that what we are observing in the lab, that we are going to use. Okay, and in this case we are talking about plain concrete, so it's not having any reinforcement. Okay, so it's a plain concrete, reinforcement is zero. Okay, so now let's see how do we do this. Okay, now I'm choosing a small value of strain 0.001. So you can see now for concrete in compression we have already seen this. Okay, so this kind of sustained curve behavior we are going to find. Now if you look at it, so, and we have taken 35 megapascal. So what is this? This is your F prime C, which is 35 megapascal, and this FC, this is your epsilon C. Okay, now where is the strain value that I'm taking? I'm taking a strain value of, let's say, here. Okay, so what is this value? Which is 0.001, and this is your epsilon prime C, which is 0.002, which is also taken as epsilon prime C. Okay, So we are doing this calculation when concrete is at a strain of 0.001. Okay. Now let's see how the system is going to behave. I'm going to erase this, and we will do the calculation anyway after completing this, describing this behavior. Okay. Right. So this is your parabolic stress strain curve relationship that what we are using. Now what is the diagram? Epsilon C value, I have taken it as 0.001. What is your epsilon prime C? Which is 0.002, right? So if you plug it in your constitutive equation, that is your Hockney-Stadt strain curve, for a strain of 0.001, for a 35 megapascal strength concrete, you get a stress of 26.25 megapascal. Similarly, now we can calculate now I got the stress in the concrete. Let us, and we don't have any steel. So steel is zero, right? So there is no steel. So only this component AS is zero. So stress, we don't need to worry about what is the stress in the steel because there is no steel, right? So the total load resistance at this strain is going to be area of concrete, which is 62500 multiplied by 26.25. You get 1640.6 kilonewton. You see, that's quite a big load. Even though it is a plain concrete, under compression, you are having very high capacity. Okay. Similarly, we can do for other calculations also, 0.002, 0.004. So when you take this 0.004, what will happen? If you plug it in this equation, you will know that the parabolic model, the stress will become zero. So that is why the load also has become zero. So you can create a simple Excel sheet and you can do this calculation. Okay. Now let us see the same member. We have talked about compression. You see, it can take about 2188 kilonewton of load for a section of 250 by 250 mm, which is having a cylinder strength of 35 megapascal. Okay, it's quite a good capacity that it can offer in compression. Now let us see what is happening in tension. So one is I'm squeezing the concrete. Now I'm pulling the concrete. So in this case, I'm taking a value of 0.00017. You can ask me why do I take this value? Because I wanted to calculate at what level it is going to crack. Now, how do I know what is the strain at which it is going to crack? So you know what is the tensile strength of concrete. If I'm taking 35 megapascal, my tensile strength is going to be 3.5 megapascal, right? So for a 3.5 megapascal, we know that concrete and tension, it is going to be linear behavior. So for 3.5 megapascal, what would be the strain in concrete in tension? So if somehow I can calculate my elastic modulus, then what we can do, 3.5 divided by EC will give me what is the strain, right? So that is what we have done. So basically, if you look at it, so this is your elastic modulus of your concrete. Now you can ask me, why did I take 35.75 in here? Because what is our equation for your EC? EC is 5000 square root of, now here FCK. FCK is characteristic strength from cube research, right? So, but now what I have is only F prime C, which is cylinder strength. And when I convert it into cube strength, I have to multiply by 1.25, okay, to get my cube strength. But this is actually the cube strength. Again, the cube strength is your mean strength. To get your FCK in your calculation, so what is characteristic strength? Only 5. I have to choose a value so that only 5% of the results will be less than that, right? That is the definition for your characteristic strength. So usually it is F prime C 1.5 minus 8 megapascal. So, or in other words, is going to be mean value minus 1.65 times 5, which is the assumed standard deviation for your normal distribution. So if you take this value, it will work out to be 35.75 megapascal. So that is why I have taken this as the elastic modulus. So in other words, this is EC multiplied by epsilon C. That is your stress. Because we know that concrete in tension is going to follow linear elastic sustained behavior until it cracks. After it cracks, there is not going to be any stress that is offered by concrete in tension, right? So this is how we got this 35.75. Okay. So anyway, I'll erase this. Right. So you get this. So we got the value of 3.5. So the applied load resistance for a strain of 0.000117 is basically 62.5 is double zero, which is the area of concrete multiplied by 3.5. So it is offering 218.8 kilometers. Now, for any strain value lesser than that, it is going to follow elastic behavior. So let's say if I take half of the strain, epsilon c is now 0.000117 divided by 2. If I take 50% of this, the load resistance will be, because elastic modulus is not going to change, so it is going to be basically directly the stress value is going to be 3.5 divided by 2. So the load resistance is also going to be half. Okay. So like this, we can also do the calculations for other strains, and you find that. So how do we get the deformation again? 0.12. This multiplied by 1000 is nothing but your deformation, because the length of the member is 1 meter. So I'm multiplying by 1000 to get 0.12 millimeter. Why I'm putting it in negative? Because in concrete usually compression is taken as positive, tension is taken as negative. So you can follow any sign convention, but be consistent. Okay, so you can see that again the deformation at a 0.12 deformation, it is offering a load of only 218. Even if I take a small a higher strain, this 0.000117, okay, what will happen? The concrete now will, when I tested in concrete in tension, you've seen that is going to go like this, and then is going to fall off. Okay, so this is your stress, and this is your strain in concrete in tension. Okay, so this value is what we have taken it as 3.5 megapascal, and this strain epsilon prime t is taken as 0.000117. Okay, so you see that the concrete is going to crack at a very small strain. So if you look at it, it's 0.000117. And what is the peak strain of concrete? It is going to crush. From design point of view, we take it as 0.0035. That is double zero only. Here it is 0.000117. So you can see that it is having a very low strain values. It can offer resistance. After that, it will crack and it will not offer any load resistance. So that is why if you look at it, at cracking, it is having, this is the maximum load this plain concrete member can offer in tension. Okay, so after that it will not offer any load resistance tension. So now if you go back to the slide, how much is the compression capacity? Roughly about 2187. Now what is the tension capacity? 218.8. So it is actually 10% of your compressive strength offered. The member also, because it doesn't have any reinforcement, it is able to take only 10% of the load that what the concrete member can take in compression. So concrete, as we have seen the material resistance, it's clearly reflecting in the member level behavior also, because after it exceeds, the strain level exceeds this cracking strain, it cannot offer any tension. So this way we can generate this entire load deformation behavior. So this is basically in compression. Okay, so this is tension. Okay, so that's why we have drawn like this. So you see here the maximum load is here, and this is the value that we have shown the calculation, and then for any other values also you can calculate. At this value it will become 0. But anyway, this is a theoretical thing. Once it reaches peak, you have seen that concrete fails in a very abrupt manner in compression. So this will happen very quickly. In fact, to get this post-peak behavior, you need to test it in a servo control machine for members to get it. Okay.